In the pocket of an average person lies a device more important than a tank. This is not an exaggeration or a metaphor. It is the literal truth of modern civilization. The smartphone in a teenager's hand contains more computing power than all of NASA's computers during the moon landing. The modern F-35 fighter jet contains more semiconductors than the entire global industry produced in the 1970s. Every mouse click, every screen swipe, every keystroke is the result of a global chain of hundreds of companies scattered across dozens of countries. And at the center of this chain is a tiny piece of silicon that has become the oil of the 21st century. Imagine an ordinary morning. A person wakes up to a smartphone alarm. There's a chip. Turns on a coffee maker with a programmable timer. Again, a chip. Gets into a car where dozens of microprocessors control everything from the engine to the entertainment system. At work, uses a computer connected through routers and servers packed with processors. In the evening, watches videos on a TV, receiving content from servers housing thousands of chips. Even the refrigerator now has a built-in computer. We are swimming in a sea of semiconductors without even realizing it. The difference between chips and oil is that oil can be pumped from various corners of the planet. Advanced microchips, however, are produced in only a few places, and this concentration has turned semiconductors into the most dangerous bottleneck of the modern economy. There are no alternative sources. There are only a few companies, a few factories, a few geographical points, and if they stop working, modern civilization would halt faster than during any oil embargo. Technology no longer just makes life easier, it is power. Whoever controls chip production controls the future of civilization. And that is precisely why a war is now unfolding that most people are not even aware of. It is a war without shots, but with sanctions. Without tanks, but with trade restrictions. Without bombs, but with technological blockades. And the stakes in this war are higher than in any military conflict of recent decades. To understand the scale of what's happening, one must first grasp what a modern microchip is. At its core is a semiconductor, a material that can conduct electricity but not as well as metal and not as poorly as an insulator. This property makes semiconductors ideal for creating electronic switches. Silicon became the standard precisely because its properties can be precisely controlled by adding impurities, a process called doping. Add phosphorus atoms and you get a material with an excess of electrons. Add boron and you create a deficit of electrons, holes, which can also carry charge. The basic element of any chip is a transistor, a tiny electronic switch that can be in the on or off position. These are the very zeros and ones on which the entire digital world runs. The first transistor, invented at Bell Labs in 1947, was the size of a palm. Today, on a chip the size of a fingernail, tens of billions of transistors fit. If the automotive industry had developed at the same pace, a modern car would cost a few cents and could circle the Earth on 1 liter of fuel. When people talk about 7 nanometers or 3 nanometers, they are not referring to the size of the chip itself, but to the size of individual elements inside it. 1 nanometer is 1/1000th of a meter. For comparison, a human hair is about 80,000 nanometers thick. A DNA molecule is about 2.5 nanometers wide. Modern transistors in chips are so small that millions of them can fit on the tip of a needle. We are talking about structures smaller than the wavelength of visible light. This is not just engineering, it is working at the boundary of the physically possible, on scales where the laws of quantum mechanics begin to take effect. Moore's law, formulated by Gordon Moore, the founder of Intel, back in 1965, predicted that the number of transistors on a chip would double approximately every 2 years. It was not a physical law, rather an observation and a forecast. But for decades, this law worked like clockwork, defining the pace of technological progress. Each new generation of chips was faster, more powerful, and more energy efficient than the previous one. Computers became cheaper, smartphones became smarter, and capabilities that seemed like science fiction yesterday fit into a pocket today. But now the industry has hit a physical limit. When elements become the size of a few atoms, quantum effects begin to manifest, making further miniaturization extremely difficult. Electrons start tunneling through barriers meant to hold them. Heat dissipation becomes a critical problem. The denser the transistors, the more heat they generate per unit area. Problems with current leakage, reliability, and variability in characteristics arise. That is why creating each new generation of chips has become a scientific feat. Developing a single advanced processor today costs several billion dollars. This is not just drawing schematics on paper. It is physics at the atomic level, chemistry of the most complex reactions, materials science of new substances, and programming billions of lines of code for verification and testing. A development team can number thousands of engineers working for years. Supercomputers are needed to simulate chip behavior even before the first prototype is created. Specialists in optics, quantum physics, thermodynamics, and mathematical modeling are required. A modern chip contains tens of billions of transistors, more than the neurons in the human cerebral cortex. The Apple M1 processor for laptops contains 16 billion transistors. The latest GPUs from NVIDIA, over 70 billion. And each of these transistors must work flawlessly, switching billions of times per second for years without a single error. This is a level of precision and reliability humanity has never before achieved in any field. A factory to produce such chips costs as much as building a small metropolis, $15 to $20 billion. And it's not just a building with equipment. These are clean rooms, where the air is thousands of times cleaner than in an operating room. They constantly maintain stable temperature, humidity, and pressure. Every speck of dust can become a defect on a chip, so the air is filtered hundreds of times per hour. Workers enter through airlocks, dressed in special suits covering every centimeter of skin. These are machines the size of buses that imprint patterns onto silicon wafers with atomic precision. These are robots that transport wafers between stations without a single human touch. These are automated control systems that check every stage of production. The chip creation process involves hundreds of steps. First, a monocrystalline silicon ingot is grown, a perfectly pure cylinder weighing hundreds of kilograms. It is sliced into thin wafers, less than a millimeter thick. These wafers are polished to a mirror shine. Then lithography begins, applying patterns layer by layer. Each layer requires applying photoresist, exposure through a mask, etching, and cleaning. The process can include over 1,000 individual operations. The output is a wafer with hundreds of chips. They are tested, cut, packaged, and tested again. And only then does the chip end up in a device. Yield, the percentage of chips that pass all tests, is a critical metric. In the production of advanced processors, it can be 50% or even lower. This means half the chips on a wafer do not work properly and are scrapped. The cost of a single wafer can reach several $1,000s, and if the yield is low, production becomes unprofitable. That is why companies that can stably produce advanced chips with high yields possess a colossal competitive advantage. The history of the globalization of the semiconductor industry is a story of how rational economic decisions led to dangerous dependence. In the mid-20th century, the United States invented the transistor at Bell Labs, the integrated circuit thanks to Jack Kilby of Texas Instruments and Robert Noyce of Fairchild Semiconductor, and the microprocessor within Intel's walls. Silicon Valley got its name precisely from silicon chips. It was a time of American dominance, when all key technologies, all patents, all production capacities were on U.S. soil. But gradually, American companies concluded that manufacturing was expensive, complex, and required enormous capital investment. In the 70s and 80s, the cost of building factories grew exponentially, while manufacturing margins shrank. Shareholders demanded profits, and investments in production ate up capital. It seemed much more profitable to focus on what brought maximum added value: design, development, innovation. And manufacturing itself could be outsourced to where labor was cheaper, taxes lower, and regulators more lenient. First, manufacturing capacity moved to Japan, which dominated memory production in the 70s and 80s. Japanese companies like Toshiba, Hitachi, NEC, and Fujitsu literally pushed Americans out of this market. They offered higher quality products at lower prices. The US government even accused the Japanese of dumping and imposed trade restrictions. But economics took its course. If it was cheaper to produce in Japan, then so be it. Then, South Korea picked up the baton. After the war, one of the world's poorest countries transformed into a technological power thanks to targeted state policy. The government selected several chaebols, large conglomerates like Samsung and LG, and provided them with loans, subsidies, and protection from competition. Samsung started with memory production in the 80s, investing giant sums even during crises when competitors cut costs. The strategy paid off. Today, Samsung and SK Hynix control a large portion of the global memory market. But the main player became Taiwan. In 1987, Taiwanese engineer Morris Chang, who had worked for 25 years at Texas Instruments, founded Taiwan's Semiconductor Manufacturing Company, TSMC. He was 56, an age when most people think about retirement, not revolutions. But Chang saw an opportunity others missed. His business model was revolutionary, not to develop its own chips, but to manufacture them for other companies. Foundry, pure manufacturing without competing with its own customers. Before TSMC, all major companies in the industry were vertically integrated. Intel designed its processors and manufactured them itself. AMD did the same. This required huge investments in both R&D and manufacturing simultaneously. Chang proposed separating these functions. Companies could focus on design without spending on building factories, while TSMC provided world-class manufacturing. For clients, this meant access to advanced technologies without capital expenditure. For TSMC, a stable flow of orders from multiple clients, allowing full capacity utilization. This model proved so successful, it changed the entire industry. A whole class of fabless companies emerged, without their own manufacturing. NVIDIA, designing graphics cards, never had a factory. Qualcomm, dominant in mobile chips, also works only on design. Apple designs processors for its iPhones and Macs, but manufactures them at TSMC. Even AMD, which used to have its own plants, spun off manufacturing into a separate company, Global Foundries, and eventually switched to TSMC entirely. Today, TSMC manufactures chips for hundreds of companies worldwide. It is the most important company in the world that most people have never heard of. Without TSMC, there would be no latest generation iPhone, no NVIDIA GPUs for artificial intelligence, no AMD processors for servers, no modern automotive controllers. The company invests over $40 billion annually in new technologies and capacity. Its factories operate around the clock, producing millions of chips every day. Its engineers solve problems that seemed impossible 5 years ago. And all this critical infrastructure is concentrated on an island with an area of 36,000 square kilometers, which China considers its territory. Taiwan is located 180 kilometers from the coast of mainland China. Beijing has never recognized the island's independence and regularly declares plans for reunification, by force if necessary. Every year, Chinese military aircraft violate Taiwanese airspace, demonstrating strength. Every year, tensions rise. Taiwan is called the Silicon Shield, an island protected not by an army, but by its irreplaceability in the global economy. 90% of the world's most advanced chips are produced there. This means any conflict in the Taiwan Strait would instantly paralyze the global economy. Smartphones, computers, cars, medical equipment, communication systems, data centers, everything would stop. Not in a month, not in a week, within days. Chip inventories in warehouses would deplete in a matter of weeks. Production lines worldwide would halt. Economic damage would exceed any crisis in history. The world has never been so vulnerable to a single geographical point. The Suez Canal can be bypassed, adding a few days to the route. The Strait of Hormuz has alternatives. Even oil fields are scattered across the planet. But there is simply no replacement for TSMC's Taiwanese factories. Building similar capacity elsewhere would take years and require hundreds of billions of dollars. And that's assuming it's possible to transfer not only equipment, but also knowledge, experience, manufacturing culture. Things money can't buy. The United States retained leadership where it is most profitable, in chip design and architecture. Intel, the company that essentially created the microprocessor industry, although it lost its former dominance, still remains the largest manufacturer of processors for personal computers and servers. But Intel's recent history is one of missed opportunities. The company missed the smartphone revolution, failing to create competitive mobile processors. It fell behind in manufacturing technology, allowing TSMC and Samsung to surge ahead. Its attempts to manufacture chips for other companies have not yet reached the scale of its competitors. Nevertheless, Intel remains a giant with tens of billions in revenue, a huge patent portfolio, and thousands of talented engineers. Under the leadership of new CEO Pat Gelsinger, the company is trying to regain technological leadership, investing hundreds of billions of dollars in new factories in the US and Europe. This is a grand bet that America needs its own advanced manufacturing again, and that Intel can provide it. The success or failure of this strategy will determine not only the company's future, but that of the entire American semiconductor industry. NVIDIA has become the most valuable company in the industry thanks to graphics processors that became the foundation for training AI systems. What began as a product for gamers turned into a critical technology for the most revolutionary field of modern science. NVIDIA's graphics cards cost tens of thousands of dollars apiece, and demand for them is so high the company literally can't produce enough. Its market capitalization exceeds $1 trillion. Founder and CEO Jensen Huang has become one of the most influential figures in the tech industry, and his conference keynotes attract thousands of spectators like rock concerts. AMD returned to the game after many years in Intel's shadow. Under the leadership of Lisa Su, a Taiwanese-American engineer, the company created the Zen architecture, which, for the first time in decades, allowed it to compete with Intel on equal footing. AMD's Ryzen processors for consumers and EPYC for servers have captured significant market share thanks to better price-to-performance ratios. AMD also competes with NVIDIA in the graphics card market, though it remains far behind in the AI segment. Its strategy is built on partnership with TSMC. AMD designs the chips, and the Taiwanese manufacture them. Qualcomm dominates in mobile chips. Its Snapdragon processors are in the vast majority of Android smartphones worldwide. The company earns not only from selling chips, but also from licensing patents related to mobile communications. Every smartphone manufacturer pays Qualcomm royalties, making it one of the most profitable businesses in the industry. But the emergence of in-house chips from Apple, Samsung, and even Google creates new challenges. Clients want independence, and Qualcomm must constantly prove its value through innovation. American strength lies in innovation, patents, and control over architectures. ARM, though formerly a British company, is controlled by American interests and uses American technology. Its processor architecture is licensed to hundreds of companies worldwide, from Apple to Chinese startups. Synopsys and Cadence provide software for chip design. Without their tools, creating a modern processor is practically impossible. The U.S. controls the intellectual foundation of the industry, and this gives Washington immense power. But the weakness is obvious: manufacturing capacity. America lost the ability to make advanced chips on its own soil. Intel is trying to regain technological leadership in manufacturing, but lags behind TSMC by several generations. Global Foundries, the company spun off from AMD, long ago abandoned the race for leading-edge processes. There is not a single factory in the U.S. capable of producing 3-nanometer chips. All American companies depend on TSMC, meaning they depend on Taiwan, meaning they depend on geopolitical stability in a region that may not have it. That is why Washington is pouring tens of billions of dollars into building new factories on American soil. The CHIPS Act, passed in 2022, allocated $52 billion for subsidies and incentives to stimulate manufacturing. TSMC is building a factory in Arizona. Samsung is investing in Texas. Intel is constructing plants in several states. This is not just industrial policy, it is a national security issue. Without its own advanced chip production, America is vulnerable. Its military systems depend on supplies from abroad. Its tech companies could be cut off from critical components. It is a risk Washington is no longer willing to tolerate. China has chosen a strategy of technological sovereignty. Beijing understands perfectly well that dependence on chip imports is a vulnerability that could be used against it. And this vulnerability is not theoretical. American sanctions have already proven how effectively a country's technological progress can be choked by cutting off access to advanced semiconductors. Chinese companies consume more semiconductors than any other country in the world. Every smartphone, computer, and TV produced in China requires chips. But most of these chips are either imported or produced using imported equipment. Semiconductor Manufacturing International Corporation, SMIC, is China's largest chip manufacturer. The company was founded in 2000 by a group of engineers led by Richard Chang, a former top manager at TSMC. From the start, SMIC was positioned as China's answer to the Taiwanese giant. For decades, the company has been catching up to leaders, investing billions in new technologies and poaching engineers from Taiwan and other countries. But the gap closed slowly. Today, SMIC lags behind TSMC by about 5 years. When the Taiwanese produce 3-nanometer chips, the Chinese are just mastering 7 nanometers. And even that they achieved with great difficulty. SMIC's 7-nanometer process is less efficient than competitors. Yield is lower, cost is higher, chip performance is worse. This doesn't mean Chinese chips are bad. They are quite suitable for many applications. But for advanced applications, AI, high-performance computing, the latest smartphones, they are not suitable. China's main problem is lithography, the process of imprinting microscopic patterns onto silicon wafers. For advanced chips, extreme ultraviolet (EUV) lithography equipment is needed, produced by only one company in the world, ASML from the Netherlands. American sanctions prohibit the sale of this equipment to China, effectively freezing its technological progress at the 7-nanometer process level. Without EUV machines, producing more advanced chips is impossible. It's not a question of money or desire, it's a physical limitation. Beijing is investing hundreds of billions of dollars in attempts to create its own lithographic technology. A national semiconductor industry fund has been created, pouring money into dozens of companies. State universities receive grants for research. Engineers from abroad are lured with high salaries and promises. But this is a task of incredible complexity. EUV technology is the result of 30 years of R&D, thousands of patents, hundreds of supplier companies. Replicating this in a few years is practically impossible. Some experts believe China could create its own EUV machine by the end of the 2020s. Others think it will take decades, if it's even possible. For now, China is forced to work with what it has. SMIC is trying to squeeze the maximum out of deep ultraviolet DUV technologies, using multiple exposures and other tricks to create smaller structures. Huawei, cut off from US technologies, developed its own processor architecture and collaborates with SMIC for their production. It's expensive, inefficient, but it works. Taiwan is TSMC and everything around it. The company controls over 50% of the global chip manufacturing market and over 90% of the market for the most advanced chips. Its market capitalization exceeds $500 billion, more than most of the world's largest corporations. But numbers don't convey its real significance. TSMC is not just a big company. It is a critical node in the global technological infrastructure. Morris Chang built not just a company, but an entire ecosystem. Around TSMC, hundreds of supplier companies grew, providing materials, equipment, tools, services. Tens of thousands of engineers who passed through TSMC spread its culture and methods throughout the industry. Taiwanese universities train specialists specifically for the semiconductor industry's needs. The government supports the industry with tax benefits and favorable regulation. TSMC was the first in the world to master the 7-nanometer process, then 5, 3, and will soon start mass production of 2-nanometer chips. The company invests over $40 billion annually, more than Intel, more than Samsung. Its factories are marvels of engineering and logistics. Fab 18, one of TSMC's newest factories, processes over 100,000 wafers per month. Each wafer goes through hundreds of processes, each of which must be performed with absolute precision. The production management system tracks millions of parameters in real time, optimizing processes for maximum efficiency. The company is known for its almost manic obsession with quality. When Apple prepares to release a new iPhone, TSMC engineers work for months to ensure perfect production of the A-series processors. Yield must be maximum, defects minimal. Each chip is tested multiple times. The slightest problem could lead to a delay of a product launch worth hundreds of millions of dollars, and TSMC does everything to avoid such situations. TSMC is the reason the whole world fears for this island. American politicians openly say that protecting Taiwan is not only a question of democracy or human rights, but also one of economic security. If Taiwan falls, the global economy would collapse faster than during any crisis in history. And everyone knows this, in Washington, Beijing, Tokyo, and Brussels. South Korea is represented by Samsung and SK Hynix, two giants of the semiconductor industry. Samsung is a huge conglomerate producing everything from smartphones to tankers. But its semiconductor division is the crown jewel. Samsung is TSMC's only real competitor in manufacturing logic chips, though it lags in quality and volume. The company invests tens of billions of dollars annually in an attempt to catch up to the Taiwanese leader. Samsung's strategy differs from TSMC's. The Koreans not only manufacture chips for others, but also design processors for their own Galaxy smartphones. This gives the advantage of vertical integration, but creates a conflict of interest. Clients fear Samsung may prioritize its own products or use their technologies for its own developments. That's why many prefer to work with TSMC, even though Samsung sometimes offers better terms. However, the Koreans absolutely dominate in memory. Samsung and SK Hynix together control over 70% of the global DRAM market, the memory without which no computer or smartphone works. They also lead the NAND flash memory market, used in SSDs and memory cards. This is an extremely profitable business, though cyclical. Memory prices can fluctuate multiple times depending on supply and demand balance. South Korea realized the strategic importance of semiconductors back in the 80s and made them a national priority. The government provided cheap loans, protection from competition, and support during crises. Samsung invested in memory even during the Asian financial crisis of 1997, when most companies were cutting costs. This counter-cyclical strategy paid off. Competitors went bankrupt or left the market, and Samsung captured a dominant position. Today, South Korea is one of the few countries with a full semiconductor industry cycle. From design to manufacturing, from memory to logic chips, from equipment to materials. This makes the country a key player in the global chip war. But its dependence on exports and proximity to North Korea create vulnerabilities that cannot be ignored. Europe lost the manufacturing race, but retained control over the most critical link in the chain: equipment. ASML from the Netherlands is a company almost no one has heard of, but without which not a single advanced chip on the planet exists. It manufactures lithography equipment, machines that imprint microscopic patterns onto silicon wafers. And in one specific category, extreme ultraviolet (EUV) lithography, ASML is an absolute monopoly. No one else in the world can make such machines. This monopoly is not accidental or the result of unfair competition. It is the consequence of 30 years of research, development, and investment. It is the result of collaboration among hundreds of companies and research centers worldwide. It is the pinnacle of human engineering thought, so complex that reproducing it is practically impossible. If ASML stopped deliveries, the entire advanced chip industry would stop within a year. New factories couldn't start operations. Existing ones couldn't transition to new technology generations. Technological progress would freeze. Besides ASML, there are other important companies in Europe. Infineon from Germany is a major manufacturer of chips for the automotive industry and industrial automation. ST Microelectronics from Italy and France specializes in analog chips and microcontrollers. NXP from the Netherlands dominates chips for contactless payments and automotive electronics. But in terms of volume and technological level, they lag far behind the leaders from Asia and the US. The European Union has announced plans to get back in the game. The European Chips Act has been passed, providing for investments of tens of billions of euros to build factories and develop domestic capacity. Intel plans to build several megafactories in Germany, costing over 30 billion euros. TSMC is considering a factory in Dresden. But Europe is decades behind, and catching up will be extremely difficult. Europe's problem is not just money, but fragmentation. 27 countries with different priorities, different regulatory systems, different industrial bases. Coordinating a common strategy under such conditions is extremely difficult. Every country wants a factory on its territory. Every government bargains for maximum subsidies. This slows decision-making and makes Europe less competitive compared to China or the US, where decisions are made centrally and quickly. The extreme ultraviolet (EUV) lithography machine is the pinnacle of human engineering. It is the size of a small bus, weighs over 200 tons, and costs more than $150 million. One machine. For comparison, that's the price of a nuclear submarine or 2 modern fighter jets. Inside it, a laser generates light with a wavelength of just 13 nanometers, dozens of times shorter than visible light. This light reflects off mirrors polished to a fraction of a nanometer and projects patterns onto a silicon wafer at a speed of 150 wafers per hour. To understand how complex this is, imagine the following. The wavelength of light determines the minimum size of features that can be imprinted on a chip. Ordinary visible light has a wavelength of 400 to 700 nanometers, too large for modern chips. Deep ultraviolet, DUV, used in the previous generation of lithography, has a wavelength of 193 nanometers, better, but insufficient for 3 or 5 nanometer processes. Extreme ultraviolet light with a 13 nanometer wavelength allows creating incredibly small features. But creating such light and using it for lithography is a task that seemed impossible just 20 years ago. EUV light is absorbed by everything, including air. This means the entire optical system must operate in a vacuum. Ordinary glass lenses cannot be used. They are opaque to EUV. Mirrors must be used, and not simple ones, but multi-layer mirrors consisting of dozens of alternating layers of molybdenum and silicon, each a few nanometers thick. These mirrors must be polished with incredible precision. If one such mirror were enlarged to the size of Germany, the largest irregularity on its surface would be the height of a person. The light source is a separate engineering problem. Inside the EUV machine, a powerful laser is focused on tiny droplets of tin, falling into a vacuum chamber at a frequency of 50,000 times per second. Each droplet, 30 microns in size, is heated by the laser to a temperature of several 100,000 degrees, hotter than the surface of the sun. The tin turns into plasma, emitting EUV light. The system must hit the laser on the fast-moving droplets with absolute precision, otherwise no light is generated. It's like shooting a rifle at a bullet flying toward you and hitting it every time. Then this light must be collected, formed into a beam, and directed through a system of mirrors onto a mask, a plate with the chip pattern, and then projected onto the silicon wafer. Every element of the optical system must be perfect. The slightest vibration, the tiniest temperature change, the smallest particle of dust, and the pattern will be distorted, the chip ruined. The machine is equipped with active stabilization systems that compensate for vibrations with sub-nanometer precision. Temperature is controlled to thousandths of a degree. Why can't such a machine simply be copied? Because behind it lies 30 years of R&D spent solving thousands of technical problems. Because it is the result of work not by one company, but by an entire global ecosystem. Mirrors for EUV systems are produced by the German company Zeiss, the result of decades of optics research. Laser systems are supplied by American Cymer, acquired by ASML. Ultra-high precision mechanical components are manufactured in Japan. Control software is the result of thousands of programmers' work. Every element is protected by patents. Every technology is the result of years of development. ASML invested over 6 billion euros in developing EUV technology before it sold the first commercial machine. That's money without a guaranteed return, pure risk. The company worked in partnership with Intel, Samsung, and TSMC, who also invested funds and provided feedback. Hundreds of research institutes worldwide participated in solving individual problems. It was a global project, comparable in complexity to creating a modern aircraft or spacecraft. Now ASML produces several dozen EUV machines per year. Each is assembled by hand by a team of highly skilled specialists over several months. Then the machine is disassembled into components, packed into 40 shipping containers and sent to the client, to Taiwan, South Korea, the US. On site, a team of ASML engineers reassembles the machine, installs it, calibrates it. The process takes months. This is not mass production like in the automotive industry. It's piecework. Each machine is unique. Without ASML, producing modern 3 and 5 nanometer chips is impossible. All alternative lithography methods hit physical limits. Companies tried using multiple exposures with DUV, imprinting the pattern several times to create smaller features. It works, but it's slow, expensive, and has limits. EUV allows creating small structures in a single pass, making production faster and cheaper. It's not just an advantage, it's a necessity for producing advanced chips. ASML is not a company in the traditional sense. It is a global consortium disguised as a corporation. Its supply chain stretches across the world, including over 5,000 suppliers. Critical components are produced by only a few companies, and there are no replacements. This creates vulnerabilities. If even one key supplier faces problems, ASML's entire production chain would stop. And if ASML stops, advanced chip production worldwide stops. This is what makes ASML both irreplaceable and vulnerable. China cannot build an ASML equivalent because it cannot reproduce this entire ecosystem. It lacks access to critical technologies protected by patents and export controls. It lacks decades of experience in optics, lasers, vacuum systems, precision mechanics. Even if China could create some analog, it would take decades and hundreds of billions of dollars, and even then with no guarantee of success. The technological gap is so vast that bridging it is practically impossible. This turns the Netherlands, a country slightly larger than a medium-sized US state, into one of the most influential countries in the world. ASML is based in the small town of Veldhoven, with fewer than 50,000 inhabitants. But decisions made at the company's headquarters affect the fates of nations. When the US asked the Netherlands not to sell EUV machines to China, the Dutch government agreed, despite potential losses. Because the US controls many of the technologies ASML uses and could block its work. Geopolitics has penetrated even the world of high technology, where it seemed only market and innovation should rule. United States sanctions against China in the semiconductor field are a new kind of war. Not tanks, not missiles, but a ban on access to technology. It is a weapon that doesn't kill people, but strangles the economy and technological progress of an entire civilization. In 2019, the Trump administration placed the Chinese telecommunications company Huawei on a blacklist, prohibiting American companies from selling it chips and technologies without special permission. Huawei was one of the world's largest tech companies, producing smartphones, telecommunications equipment, servers. The sanctions hit it like lightning. Suddenly, Huawei could not get processors from Qualcomm, software from Google, chips from Intel. The company tried to switch to its own developments, Kirin processors of its own design, Harmony OS instead of Android. But Kirin processors were manufactured by TSMC, and under US pressure, the Taiwanese company stopped supplies. Huawei found itself cut off from advanced technologies. Its smartphone business, which competed with Apple and Samsung for the top spot globally, collapsed in 2 years. Its global market share fell from 20% to a few. In 2022, the Biden administration expanded sanctions to the entire Chinese semiconductor industry. New rules banned the sale to China of any advanced chip manufacturing equipment, advanced AI chips, even technical documentation and services. American citizens and companies cannot work for Chinese semiconductor companies without special permission. This means thousands of engineers working at SMIC and other Chinese manufacturers had to resign or break the law. The sanctions weren't limited to American companies. Washington pressured allies. The Netherlands agreed not to sell ASML's EUV machines to China and to limit sales of even less advanced DUV systems. Japan banned the export of critical chip manufacturing equipment. South Korea found itself in a difficult position, economically dependent on China, but strategically tied to the US. Samsung and SK Hynix received temporary exemptions to support their factories in China, but with the understanding that long-term, they would have to choose sides. This is not just economic pressure. It is an attempt to freeze the technological progress of an entire country. Without access to advanced chips, China cannot develop AI at the US level. Chinese models like Baidu's or Alibaba's lag behind American GPT and Claude not only in algorithms, but also in computing power. Without advanced NVIDIA GPUs, training large models takes many times longer and costs more. Without modern processors, Chinese supercomputers, which once led global rankings, have slipped down. The military consequences are even more serious. Modern weapons require advanced chips. Guidance systems, radars, drones, hypersonic missiles all depend on computing power. If China lags in semiconductors, it lags in military technology. Of course, one can fight on old chips, but the advantage of an opponent with advanced electronics can be decisive. The American military knows this, and chip sanctions are part of the containment strategy. Beijing responds with import substitution programs and huge investments in its own research. The National Semiconductor Industry Fund has received hundreds of billions of dollars. New research centers are created, factories are built, specialists are lured from around the world. Chinese companies buy any equipment still available, creating stockpiles. SMIC tries to circumvent restrictions, using older equipment to produce chips that are formally not as advanced, but still powerful enough for many applications. There are signs China is partially bypassing sanctions. Chips are purchased through third countries, resold through shell companies, mislabeled. American intelligence and customs try to block these channels, but completely closing leaks is impossible. There will always be those willing to risk profit. The black market for advanced chips is growing, prices soaring multiple times. NVIDIA GPUs that officially cost $10,000 sell for $30,000 or $40,000 on the black market in China. The Taiwan factor adds an element of real danger to this war. If China attempts to take the island by force, the world will face a choice: defend Taiwan for TSMC or accept catastrophe for the global economy. The US has publicly stated it would defend the island. Biden has said several times America would intervene militarily in case of a Chinese invasion, though later the White House tried to soften these statements. But the signal was sent: Taiwan is too important to lose. Chinese military regularly conducts exercises near Taiwan. Aircraft cross the median line of the strait. Ships demonstrate strength. Beijing publicly declares plans for reunification by mid-century, using all necessary means. The Taiwanese government strengthens its defense, buys American weapons, prepares the population for a possible war. Tension rises year by year. The economic consequences of conflict would be catastrophic. According to analyst estimates, a blockade or destruction of Taiwanese factories would cost the global economy trillions of dollars. Electronics production worldwide would stop. Automotive plants would halt without controllers. Data centers could not expand or even maintain existing capacity. Smartphones would become scarce. Medical equipment requiring chips would cease production. The economy would slide into recession faster and deeper than during any crisis in history. Some analysts call this a new form of nuclear deterrence. No one can afford to lose access to Taiwanese factories. And that's what keeps all sides from escalating. The concept of mutually assured economic destruction. If China attacks Taiwan, it loses access to TSMC. If the US intervenes, it risks conflict with a nuclear power. If the world does not intervene, it loses the foundation of its technological civilization. Everyone loses, so no one makes the first move. But how long such balance can hold is unknown. History shows economic interdependence does not always prevent wars. Before World War I, Europe was more economically integrated than ever in history. No one believed countries would embark on a suicidal conflict, but they did. Rationality does not always defeat nationalism, ambition, or miscalculations. And this makes the Taiwan question the most dangerous geopolitical time bomb of modern times. The semiconductor industry is a market of over $600 billion per year, and it continues to grow at about 10% annually. But profit is distributed extremely unevenly. The highest margins are for companies involved in design and equipment, where competition is lower and barriers to entry higher. NVIDIA earns over 50% margins on its AI graphics cards. Each H100 GPU sold for $30,000 brings the company over half that amount in profit. That's more than luxury car manufacturers. ASML has margins higher than most automakers because its product is irreplaceable and competition simply doesn't exist. The company sells several dozen EUV machines per year at over $150 million each. That's billions in revenue on a limited number of units. But high prices are justified by product complexity and lack of alternatives. Clients pay because without these machines, they cannot produce advanced chips at all. Chip manufacturers earn less because their business requires enormous capital investment and operates under fierce competition. TSMC invests over $40 billion annually in new factories and equipment. That's money that must be spent today to get profit in 3 to 4 years when new production comes online. Samsung spends similar amounts. It's a race where stopping means death. If you don't invest in the next generation of technology, in 3 years you're no longer competitive. Clients leave, and you become a manufacturer of outdated chips with low margins. The industry is cyclical. Periods of shortage are followed by overproduction. Prices jump. Profitability swings. During the COVID-19 pandemic, the whole world faced a chip shortage. Automakers stopped entire plants because they couldn't get simple microcontrollers costing a few dollars. Toyota, General Motors, Volkswagen lost billions in revenue. Consumer electronics manufacturers postponed new product launches. Queues for PlayStation 5 and Xbox stretched for months. Graphics card prices soared 3 to 4 times. Money is made at all levels of the chain, and understanding this structure is critical. Chip designers like NVIDIA, AMD, Qualcomm sell intellectual property in the form of chips themselves or architecture licenses. They don't spend on factories, giving high profitability. Manufacturers like TSMC and Samsung earn on volume and technological superiority. The more advanced a process they offer, the more they can charge for production. Equipment manufacturers like ASML, Applied Materials, Lam Research sell machines for hundreds of millions with stable income streams from servicing. Materials suppliers, silicon wafers from Shin-Etsu and Sumco, chemicals from BASF and Dow, specialty gases from Air Liquide and Linde ensure constant income flows. Each factory consumes tons of materials monthly, and these companies earn on volume. It's a complex ecosystem where each element depends on others, and a break in any link paralyzes the whole chain. Investing in the semiconductor industry is not quick money. It's a long-term bet that the world's digitization will continue, that demand for computing power will grow, that technological progress won't stop. Companies in this industry fall into several categories, each with its own business model and risks. Foundry, pure manufacturers like TSMC and Samsung. They earn on volume, technological leadership, and client trust. Risks, huge capital expenditure, geopolitics, technological failures. Fabless, companies without their own manufacturing, like NVIDIA, AMD, Qualcomm. They design chips, outsource manufacturing. Less capital expenditure, higher margins, but dependence on manufacturers. Equipment. Equipment manufacturers like ASML, Applied Materials, Lam Research. High margins, technological barriers to entry, but cyclical demand. IP and EDA. Companies selling intellectual property and chip design tools. ARM sells processor architectures. Synopsys and Cadence provide design software. These companies earn on licenses and have stable income streams. Risks here are more related to technological shifts than manufacturing cycles. Main risks for an investor? Geopolitics, technological failures, and capital intensity. Any conflict around Taiwan could crash the entire industry's stocks. Failure in developing a new chip generation could cost a company billions and its market position. The need to constantly invest huge sums means even profitable companies can have cash flow problems. This is not a market for speculators. It's a strategic bet on the long-term future of technology. Artificial intelligence changed everything, and changed suddenly. Just 10 years ago, graphics processors were needed by gamers and professionals working with graphics. Today, GPUs are the foundation for training neural networks, and demand for them has exploded so much that NVIDIA can't produce enough. NVIDIA became the world's most valuable chipmaker company. What began as a product for gamers turned into a critical technology for the most revolutionary field of modern science. NVIDIA's H100 series graphics cards cost $20,000 to $30,000 apiece, and demand is so high, queues form for months ahead. Training one large language model, like GPT-4 or Claude, requires tens of thousands of GPUs working in parallel for months. Cost reaches $100 million or more, and the main portion goes to equipment and electricity. This creates a barrier to entry. Only companies with deep pockets can afford to develop advanced models. Future data centers are huge computation factories. Microsoft is building data centers specifically for OpenAI, each costing several billion dollars. Google creates its own TPU processors. Amazon developed Graviton and Trainium chips. But all of them still need NVIDIA GPUs for the most demanding tasks. One such data center can consume as much electricity as a small town, tens, sometimes hundreds of megawatts. Energy consumption becomes a critical factor. Electricity production for running AI systems requires new capacity. Companies invest in renewable energy. Using small modular nuclear reactors is considered. Cooling itself becomes an engineering problem. Traditional air cooling systems can't cope anymore. Liquid cooling must be used. The industry's environmental footprint is growing, and it's becoming a political issue. One data center can consume millions of liters of water per day. In regions suffering from drought, this causes conflicts. Companies are forced to seek a balance between computational ambitions and environmental responsibility. Artificial intelligence accelerated the chip race to a new level. Now it's about systems that can change the very nature of work, creativity, and decision-making. Whoever controls the production of chips for AI controls the future of this technology. That's why sanctions against China include strict restrictions on exporting powerful GPUs. Washington does not want Beijing to develop its own advanced AI systems. China responds by developing its own accelerators. Huawei created Ascend chips. Alibaba developed Hangguang processors. But these solutions lag behind NVIDIA by a generation or two. CUDA, NVIDIA's software platform, became the industry standard, and switching to alternatives requires rewriting millions of lines of code. This gives America a temporary advantage, but China methodically works on creating alternatives. The future of the semiconductor industry will most likely be fragmented. Globalization, which led to the dominance of a few companies and regions, is cracking. The world is moving towards creating regional ecosystems, each with its own logic and limitations. The American ecosystem will be based on returning manufacturing to the US and allies. New TSMC factories in Arizona, Intel investments, subsidies for Samsung, all these are attempts to reduce dependence on Taiwan. The Chinese ecosystem will be isolated. Beijing is creating its own supply chain, from design to manufacturing. It's expensive, long, and technologically difficult, but China has resources and political will. Chinese companies won't be able to produce chips at TSMC's level in the coming years, but they will be able to meet the basic needs of their economy. It will be a world of two standards: advanced technology in the West and catch-up development in China. Europe is trying to regain its place in the game. The European Union announced plans to invest tens of billions of euros in building factories and developing its own capacity. Intel plans to build several plants in Germany and Ireland. But Europe is decades behind, and catching up will be extremely difficult. Its strength is still in equipment and research, not in mass production. Returning factories to developed countries will change the industry's economics. Manufacturing chips in the US or Europe will be more expensive than in Asia due to higher salaries and construction costs. This means higher prices or the need for government subsidies. But geopolitical stability and independence may be worth more than economic efficiency. The world is willing to pay a premium for security. Silicon is approaching its physical limits. When transistors shrink to the size of a few atoms, quantum effects start interfering with their normal operation. Further miniaturization becomes increasingly expensive and difficult. That's why the industry is looking for new paths. Three-dimensional chips, one path. Instead of making transistors smaller, they are arranged in several layers on top of each other. This increases density and performance without needing to shrink elements. The technology is complex but already working. AMD and Intel use it in their processors. Chiplets, another approach. Instead of one monolithic chip, several small modules are created and connected together. This allows combining different technologies and reducing manufacturing defects. If one element of a large chip is defective, the whole chip is waste. With chiplets, only the defective part can be replaced. Quantum computers promise a revolution, but are still in early stages of development. They operate on completely different principles, using quantum bits instead of classical transistors. For certain tasks, cryptography, molecular modeling, optimization, they can be millions of times faster than ordinary computers. But practical application is years, if not decades, away. Photonic technologies use light instead of electricity to transmit data inside a chip. This could solve the problem of power consumption and data transfer speed. Research is ongoing, prototypes exist, but mass production is far off. New materials, graphene, gallium nitride, molybdenum disulfide, promise improved characteristics compared to silicon, but require creating completely new manufacturing processes. Who ultimately controls the future? Not countries, although they play a huge role through regulation and subsidies. Not corporations, although they create technologies. Control belongs to supply chains, complex, global, interdependent networks that cannot be quickly reproduced or replaced. ASML controls lithography, TSMC, advanced manufacturing, NVIDIA, AI architecture. Each of these companies is a node without which the whole system doesn't work. Power is measured not by the number of missiles or army size. Power is the ability to produce 3-nanometer chips. It's control over technologies that make everything else possible. It's engineers who know how to create a lithography mask with billions of details. It's physicists who understand how to control light with a wavelength of a few nanometers. It's programmers who design architectures of billions of transistors. We live in an era where power is measured by the number of transistors per square millimeter. The country that can produce the most advanced chips can build the most advanced weapons, the most powerful AI systems, the most efficient economic systems. Chips are not just components. They are the foundation on which all modern civilization is built. A person picks up their smartphone, checks email, watches a video, chats with friends. They don't think that this device is the result of a global battle for technological dominance. They don't know about factories in Taiwan working around the clock. They haven't heard of a Dutch company that makes machines more expensive than airplanes. They don't suspect that their screen swipe is the result of a hidden war determining the world's future. Every click is politics. Every processor is geopolitics. Every transistor is the result of investments, research, diplomacy, and sometimes sanctions. The world has become so complex and interconnected that a simple chip has turned into a weapon, a shield, a currency of power. The battle for chips is not just industrial competition. It is a battle for the very architecture of future civilization. Who will win this war? It's unknown. Perhaps there will be no winners at all, but a new equilibrium based on mutual dependence and caution. Or the world will split into technological blocks, each with its own standards and limitations. Or a technological breakthrough will occur that changes the whole game. A new material, a new computing principle, a new paradigm. But one thing is clear. Whoever controls the chips controls the future. And this war is just beginning.